New measurements suggest we have made a fundamental error about the universe. God damn it, Mr. Smith.
Fundamental.
Everything is wrong.
It could be.
Fundamental means everything, right? It means like root level type shit, like big deal.
Man, are they going to tell me?
It's from the Independent.
That'd be like fundamental would be like gravity. And
that's a
stuff
big
like
deal.
That. Yeah.
Yeah. Gravity's actually two forces. I don't know why I'm saying that. Like I heard that.
It's like cheese and pizza is what it is.
It's like the cheese on the pizza.
Two forces.
Scientists have long been grappling with problems with the Hubble constant, which measures the rate the universe is expanding.
Yeah, I could give a real quick recap on that.
Let's do it, baby.
About 1993, Saul Perlmutter was heading a team where he was studying Cepheid varied stars, Type 1A and supernovas and stuff like that.
That's a badass. Anybody named Perlmutter?
Saul Perlmutter.
He's going to have like a giant pirate earring and a scimitar and a BMW. Like he's...
Yeah, 1993, and they were doing calculations, and they discovered that not only was the universe accelerating or expanding, but it was getting faster and faster. It was accelerating. And that's when the whole idea of dark energy started coming out from 93 on with their discovery.
They're like, what's feeding that?
Yeah. And they didn't know, but the measurements they were doing with those particular kinds of stars and supernova was key to understanding that it was accelerating faster and faster.
Okay, good deal. So they don't know why it's doing it, so they called it dark matter because
dark energy.
Dark energy.
Yeah.
Okay. And dark meaning that they don't know what the fuck
we
it
don't
is.
know.
Not that it's like black or absolute light or whatever.
Yeah, just some mysterious energy pushing things apart.
A new set of measurements suggests that we may have made a mistake about the fundamental nature of the universe. Researchers have found... Didn't want to burp straight into the mic.
Oh, and real quick...
I had buffalo chicken wings tonight, baby.
Ooh.
Oh, good stuff. Yeah.
Before Saul Perlmutter, there was, of course, Professor Hubble, who famously left photograph slides or negatives in film in a telescope when he went on vacation for like a weekend. Yeah, he saw stuff beyond our galaxy for the first time. Okay, so like as far as we knew before that, there was just the galaxy. There wasn't like a universe, but we knew we lived in a galaxy, right? That was the first time that we seen other galaxies.
Oh yeah, that's right. They thought everything past that was just empty.
Yeah,
and it was just.
And then they found out there was billions of galaxies, right? But the first ones they seen were on his slides because the exposure was so long it actually brightened up enough where you could see him. And they noticed that when they used spectrometry to measure the light, that it was all redshifted, meaning that the light coming from those objects was elongated into the red spectrum as opposed to compressed into the blue, meaning that it was traveling away at great speed. So, and the further away an object was, the more redshifted it was, meaning that it was expanding faster on the outside. Then in 93... So for a long time, between that time and 93, there was a big argument as to whether or not things were going to just continue to expand into nothingness, or if there would be what was called the big crunch, where gravity would pull shit back together.
Like everything's going to go...
Right.
Just keep doing this sort of...
Exactly. Or if it's just going to spread out like an explosion, right? So they started trying to measure how much mass was in the universe so they could calculate the gravity to see if there was going to be enough gravity to pull the mass back together. That's when they started studying things like neutrinos. And somewhere like in 93, 94, there was a scientific experiment set up outside of a nuclear reactor where they were looking for neutrinos.
Tachyon particles. No.
Neutrinos.
Okay.
Because tachyons are the ones supposed to travel faster than light. But they wanted to know if neutrinos had mass.
I only said that as a Star Trek reference. I didn't realize that that's a real thing.
Yeah, it's a theoretical particle that's supposed to travel faster than light. Like some particles are vector particles traveling at the speed of light. But there's
Geordi LaForge did a lot of shit with them.
Yeah. Oh, yeah.
Just saying.
But they ended up finding out that neutrinos had mass, and they did more calculations. But anyways, in 93... they came up with other calculations that said that it doesn't matter how much mass is in the universe. It's expanding faster and faster. It's definitely not going to come back into a big crunch. And now this.
Researchers have found yet more evidence that our measure of the Hubble constant, which represents radiation, is very wrong. The new findings come after research used a set of radio telescopes to create new, precise measurements of the rate at which the universe is expanding. But they found there was a discrepancy between the previously measured value of the Hubble constant and the value that is predicted by the model that comes from the cosmic microwave background radiation from the Planck satellite.
So
Max Planck.
Yeah, at first there was
Super tiny
WMAP.
shit.
At first there was WMAP, and then there was Planck satellite, and both of them measured the cosmic microwave background radiation, which
Okay.
is the heat left over from the Big Bang. And that was first discovered by these AT&T guys that built this big antenna for AT&T.
And accidentally tried to start World War III with it.
No, there was like a band frequency which was providing static, and they couldn't figure out where the hell it was coming from. No matter where they aimed it at, there was like this static. So they thought it was the equipment, and they checked all that. Nope, it was working perfectly. They even got down to where they thought it was these doves, these birds that had
Right.
built nests inside, so they cleaned that all out. Turns out they were reading the heat signature from the big birth of the universe, and that you were never going to get rid of that.
It's a constant.
Yeah,
So build a filter.
yeah. And that's what the cosmic microwave background radiation is, that was first visualized by WMAP and then later this satellite to a much larger degree.
Is it Brian Greene? He's English, younger guy,
Yeah, I
a
know he is.
physicist.
Yeah.
Is that his name, Brian Greene?
I believe so, yeah.
I seen an interview with him one time where he was in a. They were like having a debate about the Big Bang Theory or Big Bang, not the TV show, and somebody was talking about it's a theory, da 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 da, and he's like he stopped him and he goes no, he's like it's not a theory. It's literally, you can fucking see it. It's not
Yeah.
a theory.
Yeah.
It's right there. Like, we can totally see it. So you can't say it's a theory anymore.
What's the problem with it is that when you look at the microwave background radiation and you compare the homogeny of how it looks with the way that the universe is spaced out,
Right.
they can't explain how that worked, right? Still, right. So they know.
Well, they can't explain it without bending the laws of physics to do so, right?
Yes, and the guy that did that was Alan Guth, and he came up with a part of that theory of the Big Bang Theory that was called inflation. And it was a point at which, right after the birth of the universe, when it exploded from that singularity, that it actually traveled faster than light, the only time in the universe, and then somehow stopped. So there's no explanation for how it did it or how it stopped. But if that happened, that would explain how it looks now when we're looking at it. But without that explanation, we don't know how it got from that to this very clearly at all. So that's what people will poke at when they say it's just a theory. They'll bring out Alan Guth's inflation a lot of times and say, look, nothing in the universe travels faster than the speed of light. How could that have happened? And if it did happen, how did it stop?
Yeah, but we're kind of past that point, right? We know things travel faster than the speed of light. Quantum entangled things, information can travel faster than the speed of light.
But this would have
So you can't say nothing can travel faster than the speed of light anymore.
And then, of course,
right?
there's the tachyon particles, which are theoretical particles. Yeah, so, I mean, it's not an unfounded theory, inflation isn't. I mean, he did the math. He's not a dumb guy or nothing. And I don't.
I guess not.
Yeah, I mean, I don't
bet
necessarily
they named,
disagree.
Parts of universities after
Maybe
him.
so. I don't know.
Just saying.
But no. I mean, you're right. There is some evidence that points to the possibility that it could happen. They just haven't mapped it out to people's satisfaction yet.
It says that suggests there may indeed be something wrong with the standard model we use to describe the fundamental nature of the universe. For years, scientists have grasped with that potential problem and wondered whether it was the result of mismeasurement or something more profoundly wrong with the model itself. Quote, we find that galaxies are nearer than predicted by the standard model of cosmology, corroborating a problem identified in other types of distance measurements. There have been debate over whether this problem lies in the model itself or if the measurements used to test it. Our work uses a distance measurement technique completely independent from all others, and we reinforce the disparity between measured and predicted values. It is likely that the basic cosmological model involved in the predictions is the problem, said James Bratz of the National Radio Astronomy Observatory. Well, I bet he knows what he's fucking talking about. The new measurements were in line with previous measurements, suggesting those were correct, but notably different from the value predicted by modeling. Quote, our measurement of the Hubble constant is very close to other recent measurements and statistically very different from the predictions based on the CMB and the standard cosmological model. All indications are that the standard model needs revision, said Bratz. Well, that was a long way to get there.
Yeah.
He's very very, what do you call it, like thorough. There are a variety of ways that the model could be adjusted to attempt to resolve the differences. This could include alterations to the way we understand dark energy, differences in our model of particle physics, or even more exotic possibilities. Ooh, now we're getting into the good stuff.
Yeah, so the model of particle physics would be things like vacuum particles expanding space, and then the more exotic possibilities would be things like the tachyons and stuff.
Okay, now they're going to tell me something that I'm not even going to... Okay. Predictions of the Hubble constant from models suggest that it should be about 67.4 per second per megaparsec.
I can make the Kessel run in less than 12 parsecs.
That's exactly what I'm thinking. Where's the Millennium Falcon? That is derived by looking at the leftover radiation from the Big Bang and using our standard cosmological model of the universe.
So see, this is what they're saying. They're looking at the cosmic background radiation, as I said, what the cosmic SCBM is what they were calling it, right? They're looking at that and the homogeneity of that, and they're looking at the measurements that's done with like Cepheid variance, because we use parallaxis and then lasers and then other methods, and eventually we get out to doing the type 1A supernovas for measuring distances.
Okay.
So we have these different methods. They've came up with something else.
And they're saying that their measurement method is more accurate or something, right?
Yeah, but it was very close to the normal.
Now the models will have to be adjusted because there's new data. There's new...
Yeah.
And if those adjustments may fix some shit.
It's starting to be another exciting time in astronomy.
All of a sudden.
Physics, yeah.
Says, but most measurements of the Hubble constant, which uses techniques such as standard candles, which looks at the
type one, yeah.
Yeah, it looks at the brightness of objects to understand how far away they are, have produced readings of about 73 to 74 megaparsecs per decimeter or whatever. The latest research used radio telescopes and novel techniques to understand the Hubble constant with even more precision. They came up with a value of 73.9. Okay. We're down to a tenth of a megaparsec. That's it? That's the fucking article?
We got some new measurements. Things might be wrong. We're not sure.
We're going to have to run all this shit through the standard model thinkometer. Big think. They're going to go build big think.
Big think and deep thought. And then Earth.
What was the answer to life, universe, and everything?
42?
It was 42. Not 7. It might have been 73.9.
Yeah. Atoms could have been correct.
Just saying.